Okay, so this is going to be different than yesterday's talk. Because yesterday was the high level, the overview, what is an AGN? And as I started out, what is not an AGN, how are AGNs discovered, and so forth. Now, how do AGNs work? So I'm going to start with that today. I mentioned it a bit last time about black holes. And so we're going to talk about black hole properties, what evidence we have for supermassive black holes, and how we estimate the black hole properties. And by the way, you may be familiar with this particular image. Has anybody not seen this? Okay. So, is this an image of a black hole? No. Why? Because it's a black hole. You can't take an image of a black hole. I was telling Hanato there was a woman in a bar that was arguing with me. They took an image of a black hole and said, well, that's not really an image of a black hole. I said, yes, it's an image of a black hole. I said, well, really, it's not. I said, what do you know about black holes?
There is a black hole in the center.
Then at that point, you just shut up. So what it is, this is taken the event horizon interferometric image. This is actually a beautiful thing because artists have been making artists' conception of what the region around a black hole looks like. And really, it looks very much like this. So what you have here is you've got an accretion disk. And you can see the brightening on one side and the faintness on the other side. The thing in the middle, basically, somewhere in the middle of this, there's a black hole. And outside the black hole is something, the event horizon here. And so this shows the predicted relativistic effects that would make this particular appearance of this disk of gas, this accretion disk around this black hole. This is interesting because this is a black hole in, look at this, that one? Inside something I showed you yesterday. This is inside an FR1 radio galaxy, M87, which is the one that had a very prominent jet. So whatever makes that jet has to do with the physics of this very small region. And so this is very interesting because I think I mentioned yesterday the idea of how jets are specifically created is still not completely understood. It's connected with the black hole's accretion disk, with the spin of the black hole, with magnetic fields. But now you can look at this, understand the jet, and because of the nature of this image, what we understand now about this black hole, you can get some of these parameters and perhaps trace the jet back to its origin, which was not doable before. A couple other things, just out of just pure curiosity. This is in an elliptical galaxy that does not have a lot of gas and dust in the way. Remember I showed you the funny picture of the torus thing and the blocking of the light and type 2 stuff and the gas in Seyfert galaxies? Well, it's hard to look through that material. That absorbs light. But in an old galaxy, with an old stellar population and no gas, you can get a direct view inside pretty well. And so using this radio interferometry, they're able to get in and take this image. Yeah?
If it was an activity galactic nuclei, how this picture would be?
Sorry?
If it was an AGN, how the picture would be?
Oh, it would be hard to get this kind of detail just because you have to have a particular angle to look at it. If you're looking straight, there are ways you can look straight down and get to it. But if you're at any kind of like inclined thing, where you're looking through either the material surrounding this region or through the disk of the galaxy itself, it would be hard to get this kind of an image. But what's in there, if you could see it, would look like this. Okay? And that's my talk. I'm done. Okay. So, how do you make black holes? I think, Mark, you already told them how to make black holes, right? Well, you start out with stars. And so, when stars evolve, basically what happens is their internal processes of fueling, which is fusion, stop at some point. And at that point, the core of the star where the fusion activity is taking place begins to collapse because of gravitation. And the pressure can't keep it from collapsing. And in the earlier stages, of this, stars burn, as they say, different fuels inside. They convert hydrogen to helium, and helium to carbon, and then carbon to other things. And eventually, they run out of things until you get to iron. And you cannot fuse iron nuclei and get energy out of it because of the binding energy of the iron nucleus, and things collapse. That only happens to the most massive stars that have massive cores. Others stop at other stages. The sun will form something called a white dwarf at the end of its period of time, in which case the core will collapse and become what is called an electron degenerate gas. But that electron degenerate pressure, I'm not going to go into it now, keeps the thing from collapsing gravitationally. More massive stars than the sun, they will explode and form a neutron star. What will happen is, as the core collapses, in a very simplistic way, neutrons will be formed by the combination or fusion of combining of electrons and protons. By the way, that gives off a burst of neutrinos, and in 1987 there was a supernova explosion, and they were able to detect the neutrino burst from the combining of the electrons and protons forming the neutron core. And so the neutrons also have a degenerate pressure. This is statistics from mechanics I'm not going to go into, but that holds up the thing from gravitation. But if they're even more massive, the collapse cannot be stopped. And so if you have an iron core of a massive star, you can't make any more energy out of it. If it's massive enough, it passes the point of electron degenerate pressure, neutron degenerate pressure, and collapses to what they believe is a singularity, something that physically has no volume and an infinite density. And that happens for very massive stars, things that are like more than 3 times the mass of the sun, for example. And these things have been known for a while. This is a Cygnus X1. It's a well-studied X-ray system. It's a binary system. So there's a star here and also this black hole thing here. You can see that's an artist's depiction that looks exactly like the black hole of an accretion disk from M87. So this is just on the stellar scale, but the physics is the same. And what happens is gas from here, the star expands outwards and crosses what a potential point, and then spirals towards this black hole and makes this hot disk. And we see these things. So a number of these. Oh, by the way, you can get the mass of this just from Newtonian physics and Kepler's laws. You can actually see these things move around each other. You can't see this thing, but from the motion of the other star, you can actually determine what the mass of the thing is moving around or co-moving with. So we know about these things, and there's quite a number of them. And by the way, when I get to the end of the talk, I'll talk about detections of gravitational waves. The gravitational wave detections are things that are bigger than this, but probably comparable to what you can make for stellar-sized mass black holes earlier in the history of the universe. It depends on the type of stars that are making them. But again, here we're talking a few solar masses. The ones that we detected gravitational waves from are in the order of tens of solar masses. That's not what's inside an active galaxy. It presents something of a problem. So to continue, again, Martin told you all about general relativity, so I'll just go very quickly through these things. Basically, the mass produces a curvature of space-time. Massless particles or photons follow what's called geodesics. So the geodesics basically are curved paths in the presence of the mass. And this goes back to the 1919 solar eclipse, and there's a poster, but wasn't that here? That the experiment was done to test Einstein's theory of general relativity was done like right here. Not right here, but associated with the National Observatory back then. And there's a nice poster of it outside. And basically, it's been retested and reproven that the light from stars behind the sun were bent around the sun and follow geodesics. And according to this sort of the picture, you can see. But there's more to it than that. Now you're going to go back to Einstein's field theories, and you can look at these things. Here's a simple equation here that relates the R, which is the Riemann curvature tensor, or T is the stress energy tensor. This is basically all kind of tensor, field equations done in tensor form. But this G, U, mu, V term is really what we're interested in here. This defines the metric. The metric is what's related to the geodesics that we were talking about, the paths that photons would follow. So if you go far away from any kind of mass, space is Euclidean. So basically any of the lines that follow a photon would follow is essentially a perfectly straight line with no curvature whatsoever. You could represent this by one of these metrics. This can go back to Einstein's theory. So this is the Minkowski metric. And this is, this geodesic defined by this ds squared thing is equal to some minus dt squared, dr squared, and r squared, d omega squared. And that's basically a spherical coordinates here for this. And this is basically solid angle defined in here. This just breaks down to what you would get, basically just Euclidean space. But once you put a mass inside, you have to change the metric. And so the first of these was solved by Schwarzschild in, I think, 1916 or something like that. It was right after Einstein published his theory of general relativity, which I think was 1915. And, but he published it without the detailed tensor equations that required to form this metric, and that waited for Schwarzschild, who was a mathematical physicist, who I think died in World War I, if I recall. In any case, this is the Schwarzschild metric. This is a spherically symmetric static body. So it is a black hole that is just sitting there, or a massive body. It's going to be a black hole, but a massive body that's just sitting in space and in space-time around it. Okay, and then you change the Minkowski metric to this, and you can see there are these terms here. I'm sorry about the format here, but it's the best I could do. So this is like, just to let you know, it's 2gm over rc squared. G is the gravitational constant, m is the mass of the massive body, c is the speed of light, and the rest of the parameters are defined as here. You can see the differences. And so, very simply, if you let m go to 0 or you let r go to infinity, you recover the Minkowski metric. So there's no mass, or you're very far away from it, space becomes Euclidean again. But close up, it follows this particular metric. Now you can define a few other things. At some radius equal to 2gm over c squared, what you get is an event horizon. This is the Schwarzschild radius. This is actually a physically measurable thing in space, potentially. The black hole itself is a singularity. It has no dimensions. But if you have a static black hole, one dimension you have is the event horizon. It's essentially the point any photon that is released inside that event horizon follows essentially closed geodesics and never gets out again. Outside the event horizon, it still will follow curved space-time because of the presence of mass. Gives you the Schwarzschild metric in the terms in here, but it will escape. Other things will happen to it, but it will escape. So this is, if you like, inside this, you're at the point of no return. So to continue from there, so if you go back to this particular idea, you can think of, for a fixed position and angle, you can define a shell. So you can define a series of consecutive shells around the black hole. One of them could have the Schwarzschild radius if you like, or they could have two completely separate radii. And you can write the metric as d tau, dt being far away, and d tau is the proper time here, if you remember your relativity. And the dt for each shell is given by this particular term here, which you can relate back to the metric. The most important thing is if you go between two radii, you get a change in the incremental time parameter for the shells. And so you can say if R2 is equal to 8 times gm over c squared, remember 2gm over c squared is the Schwarzschild radius, is that, and that R1 was 4 times this, you can look at the difference, the delta in time, the dt between the two shells, and it comes out, you plug the numbers in, 1.2. Now this relates to an actual difference in time. So it turns out between the shells, you get different times, that is different periods for light emitted. Which means basically, the photon gets shifted to longer wavelengths as it's moving away from the central mass from point R1 to point R2. This produces, since the times or periods change, the wavelengths change, period gets longer, the wavelengths get longer, So therefore, you can think of this in terms of the light being shifted to the red. So as the photon is attempting to escape from this very deep, defined in relativity potential well here, its wavelengths are shifted to longer wavelengths, and you get a gravitational redshift. This is opposed to the motion, the redshifts you get from Doppler motion. So basically, it's essentially the light's wavelengths get stretched out as you try to escape from the central potential. This would be outside the event horizon. So the photons can escape, but they are gravitationally redshifted in their escape. This turns out to be a potentially observable effect and a very strong signature of gas close to the event horizon of the black hole. Okay, now getting back, if you've ever looked at a general relativity text, they do things just to make things simpler, which actually makes things more obscure, which they set a lot of constants equal to 1. And then to get it physically, you got to figure out what they were. But to entertain you here, we can set the speed of light equal to 1 in this context and go back. At that point, the Schwarzschild radius becomes just 2 times gm, and you can rewrite the metric in this form. And basically, all I've done here is I've taken the c's and set it equal to 1. I'm doing that just because I want to compare it to another metric for which that was done. Now it's equal to 1. And so this, again, gives you the Schwarzschild metric. This is a static black hole. But that's really probably not the most common or realistic consequence of black holes. Basically, just to get it, black holes can have mass. They could have charge, although that would be unusual that they would have charge, that we have positive charges or negative charges glommed together somehow. So there's some net non-zero charge in the black hole. But they can also have angular momentum, and that's something that's more realistic. And why? Remember the first slide I showed you, the black hole in the stellar size context is from a collapsing star. What do stars do typically? Stars rotate. As you collapse, you're going to rotate faster because you can conserve angular momentum. So the angular momentum you had when the system collapsed will be conserved as you go from a star to a black hole. So clearly, black holes should have angular momentum. So there should be some spin associated with them. But it becomes much more complicated. Actually, if you're interested in seeing what Kerr did, you can go look it up on your own. It is a very messy calculation. And again, many years later, after Schwarzschild done his Kerr in 1963, included angular momentum, and he got this Mesker metric. And it got all these terms, these deltas here, R, and some other term A, and some term rho here, and this is equal to A, some cosine theta, and you'll see what theta is in a minute. This is a mess. If you set, again, your spin back to 0, you get back to the Schwarzschild metric. So what is A? A is the important parameter here, and it's the ratio of J over M, where J in these funny units is the angular momentum of the black hole, and M is the mass of the black hole. So if you're quick here, you can see if A is equal to 0, and you plug that back in here, you get this. So this is the important term here. So, and I'm going to show you a little bit about this later, hopefully I get to it, that finding what A is not particularly simple, but it's fundamental to our understanding of the physics of black holes and AGN. So the spin of the black hole is a critical thing. It's unrealistic to assume that there is no angular momentum. But the amount of angular momentum you have may depend on the evolution of the system, the age of the black hole, and what's happened to it, the consequences of what's happened as mass is accumulated over time. But this is the important thing here, so this is one of the prime things that you would look for if you're studying these systems to determine black hole spin. If anyone has questions, please stop me. Stop me before I say anything else. Okay. Again, as I repeat what I said the other day. If J is greater than 0, then you change the physics of the region around the black hole. All right? So if you have a static black hole, you can think of the thing as purely a spherically symmetric system defined by the event horizon, which is basically proportional to the mass of the black hole. Very simple. Then you get this. And you can define Schwarzschild radius. Here's 3.5 times the Schwarzschild radius. You have the event horizon down here, singularities down here, some photon sphere here, which I'm not going to go into. but basically a totally spherically symmetric system. Once it starts spinning, it remains axially symmetric, but it's no longer spherically symmetric. So this is a Schwarzschild black hole. This is a Kerr black hole. The axis of rotation going this way. You can define inner and outer event horizons, and something called the ergosphere that I'll get to in a minute, and also the singularity. I'm going to point this out. The singularity here is a dot. I mean, that doesn't really have any physical size. But if you've got a system with angular momentum, the singularity is not a point, because a point can't have angular momentum associated with it. So the singularity becomes what's called a ring singularity, and that's what's being shown here. You can see how the system works, and there's a theta parameter here which defines where you are relative to this axis. And if you go back to the Kerr metric, you can see theta goes from 0 to, say, pi, which you get here in terms of the distribution of these components of the system around the black hole. What this is really defining are not physical things, but regions of influence of the black hole. Okay? So we'll continue. So, now, we talk about the event horizon for a Schwarzschild black hole is just 2gm over c squared, but for with c equals 1 again, for a Kerr black hole, it's somewhat different. It's equal to this, which is gm minus gm squared, g squared, minus a squared to the 1/2 power. Noting if gm is greater than or equal to a, and a is equal to j over m, and also j max goes up to about 0.998 times gm squared, all right, in this system. So then, but that thing around the event horizon, the so-called ergosphere of the Kerr black hole system, can be defined with an inner and outer radius equal to this. And you can see, of course, as theta changes, then the size of the radius changes, and that gives you that kind of ellipsoid shape that was shown in the previous slide, which it just says down here. Okay. All right. So, in any case, there are consequences if you have a Kerr black hole. One is the Penrose effect. So, with a Schwarzschild black hole, you're either inside the event horizon or outside the event horizon. If you're outside the event horizon, you suffer from gravitational redshift. You're inside the event horizon, you can't get out. Okay? But if you have a spinning black hole and you're in this ergosphere, you can have the Penrose effect. That's particle splitting. You get spontaneous creation of particles and antiparticles, and that can actually affect the black hole. Particles can escape from the ergosphere, or photons can escape from the ergosphere. Their mirror particle can get inside the event horizon, but because those particles would have to have negative energy to account for the positive energy of the escape particle, you're adding negative energy to the black hole. So the Penrose effect over time will decrease the mass of the black hole by adding negative energy, noting that energy and mass are equivalent. I don't think anybody's ever detected anything that even vaguely could be called the Penrose effect. It was interesting from a physics standpoint, but not particularly useful. The Blandford-Sniagic effect, this is much more important. Yeah?
If you add negative energy to the black hole, that doesn't mean the mass will decrease, and consequently the region of influence should decrease
Yes.
also.
Yeah. As a matter of fact, if you have really tiny black holes and you've got a Penrose effect, I mean, black holes become less and less, their stability over time can change. So tiny black holes are predicted by Hawkins to be evaporating right now in bursts of gamma rays. By the way, they're not, so there's something wrong with that. But over time, if this really works, you should decrease the mass of the black hole in its region of influence by adding the negative energy. Again, because you've got to conserve the energy from the two particles that you create. The other part of the Blandford-Sniagic, how do you say that? You were in Russia.
That's not Russian.
What is it? Czech? Polk? I don't know. I look for you for expertise. In any case, this has to relate to jets, the Blandford-Sniagic effect. Again, you have the black hole, you have the influencing space-time around it. Outside the event horizon is the Kerr black hole, and this effect, the dragging space-time with it as the black hole rotates, will cause magnetic field lines to essentially spin up close to the black hole, and that possibly creates the acceleration of and collimation of relativistic particles that produce those radio jets that I showed you yesterday. So So that, again, is related to spin. So it would be very interesting if they could determine the spin of that black hole in M87, noting that it has a very powerful jet. Because if it's not spinning and you got a jet, there's something wrong with this. Or if it's spinning very slowly, because somehow you have to have a powerful jet created. So here's a picture again of what I was talking about, the various regions and radii for a Kerr black hole, kind of a better schematic than the small one I showed you before. And you can see you have an axis of symmetry, the event horizon, and the size of the ergosphere match up here at the poles where that theta term basically goes to 0 in the Kerr metric. You've got your ergosphere inner and outer parts defined here. You've got event horizon inner and outer parts defined there. And inside here is your ring singularity, which replaces the point singularity in a rotating system. Okay? So that's what we think we're dealing with. And again, this is a region of great interest, the ergosphere here. And also the rotation of this can have effects on space-time in the region around the black hole and may be connected with creation of radio jets. All right. Now getting back to the Schwarzschild black hole, you can figure out where the stable orbits are. I was talking about spin before, and one of the things you need to figure out is how close you can get material that can emit photons that can be detected, how close that gas can be to the black hole itself. It turns out the proximity of that inner part of the accretion disk, the stable zone at the inner part of the accretion disk, could potentially be detected and would tell you what kind of black hole you got, if you knew what the mass of the black hole was. We'll get to that in a second. All right, so what you can look at here is the effective potential. And if you have mechanics classes or some relativity, you've seen effective potentials with or without relativistic terms added on. The first two parts here being kind of standard classical effective potential. Mass and little L here, the mass and angular part, the mass and angular momentum of a particle, not the black hole anymore. All right, and the particle could be, and if you wish, you could say that we're talking about a gas particle in the accretion disk in this particular case. And you know your basic physics, and you get if the derivative of the potential is 0 and the second derivative is greater than 0, then you're in a stable point. And you can look at the stable points for a Schwarzschild black hole. It breaks down to this, and then this doesn't define the smallest one. You've got this square root term in here. This is just the solution to this equation, or these based on these derivative and second derivative, and finding r and plugging it back in again. You get that r is L squared over on r squared m squared c squared, and if you just look back, this turns out to be 3 times the Schwarzschild radius. So, so that's how close you can get with a static black hole. Okay. But what about a non-static black hole? Okay, for a Kerr black hole, the radius becomes a somewhat more complicated formula. Looking like this, I'm going back again to the effective potential for a Kerr black hole that I didn't show you. You get these z terms that are these algebraic messes, where x is equal to a over m. A is defined before, proportional to the spin, the angular momentum. So for a Schwarzschild black hole, a is 0, z1 is 3, z2 is 3, and r is equal to 3 times rs. So good that everything goes back to where we should have been before when you set the spin to 0. In the cases where the spin is not 0, you can have two cases. For retrograde motion, r is equal to 4.5 times rs. For prograde, I'm going to tell you what retrograde and prograde mean in a second. Prograde motion, r goes to rs, where r is the Schwarzschild radius. Okay? So if the disk and the black hole rotate in the same direction, that means the innermost stable radius approaches the Schwarzschild radius. So by retrograde, disk spinning in one way, the black hole spinning the other way. Prograde, they're both spinning, the angular momentum vectors are in the same direction. Okay? So that means that you can get closer than 3rs for Schwarzschild. You can approach rs Schwarzschild radius for a Kerr black hole. That means the innermost stable orbit for a Kerr black hole is closer to the black hole. All right? So if you can figure out where that stuff is, then you can actually determine what the spin of the black hole is. Okay, there we go. So here's another picture of the same thing. So this is retrograde motion. This is a Schwarzschild black hole, and this is a curved black hole with prograde motion. And basically, this is X-ray emission. This signifies actually a iron K fluorescent line that I talked about a bit yet.
I think the numbers you're saying refers to a maximally spinning black hole, right?
Yeah. Yes. To approach the Schwarzschild radius requires that A over,
And 4.5 as well, right? It's a continuous.
Yeah, but the 4.5 is not particularly of interest. It's the one where you approach the Schwarzschild radius that's of interest. Because having a curved black hole, spinning black hole, where the innermost stable radius is bigger than the innermost stable radius for a Schwarzschild black hole is not a scientifically interesting result. And then couldn't really easily be distinguished. The point here is, if you said it was 4.5 rather than 3, how do you know it's spinning? You can't tell. I mean, it doesn't require that the innermost radius, the accretion disk, in a Schwarzschild black hole be 3 times, innermost radius be 3 times the Schwarzschild radius. It could be bigger. So that, again, if it's 4.5, it gets you nothing. But you're correct. And so here, this is an iron fluorescent line here. These are models of it, showing how it changes, the shape of this thing changes depending on the nature of the black hole. So it has this particular shape for a non-spinning black hole. This is the shape for retrograde motion. This particular shape, this is intensity versus energy here, for a curved black hole with prograde motion. There are a couple of things here. The peakiness of this is basically 2 Doppler effects going on here. The peakiness of that line, it should be basically a Gaussian, but it has this distorted shape because the blue wing of this thing gets Doppler boosted in your line of sight. It gives you a blue peak in all these cases. The red part has to do with what I was talking about before, which is gravitational redshift. And that's taking the line photons that are produced in the disk and shifting them to longer wavelengths as the photons escape from the central potential. So you get this red tail here, and you can see the red tail is more extreme in the prograde case. It's sort of in between in this case. In the retrograde case, there's not much of a red tail because, as I was saying, now you're at 4.5 or more Schwarzschild radio. Let me finish this point, okay? So here, if you can see this red tail, and you know what the mass of the black hole is, you can determine, by fitting this shape with a model, you can determine what it's spinning. Yeah.
Right, but if you are led to believe that you have retrograde motion, and you see that the orbit is below 4.5, then you can infer that there is no spin or there's an upper bound in the spin. So it's not irrelevant to know that.
No, well, the upper,
Is
well,
that
actually,
for signals x1 or something like this?
well, the lower bound on the spin is 0 at that point.
Only
You
if it's
can't,
prograde.
you
Only
cannot
if it's
tell,
prograde.
you cannot tell directly whether it's a static black hole or retrograde motion. There's no independent way to do that. You get the equivalent result for a static black hole if your line originates further out. I mean, you can look at these profiles. I mean, in terms of actual data, there'd be no way to distinguish between the two of them. So, also, as shown by that, the important thing is you get an accretion disk forming around the black hole. And so the classic model from Shakura and Sunyaev in '73 is a thin accretion disk. That thin basically is a measure of scale height versus radial distance. It makes a thin disk. And it assumes hydrostatic equilibrium, conservation of angular momentum, and basically the important thing is the disk viscosity. And basically what happens here is the material comes in, the velocities change with distance, of course, and basically you get viscous or frictional forces that heat up the disk as the gas rotates differentially around the central potential. And so you can define, according to the Shakura and Sunyaev model, viscosity that goes as this, or some viscosity coefficient. This is the sound speed of the gas in the disk, and h is the scale height of the disk, and the range of the coefficient is from 0 to 1. There's probably turbulence. You can invoke turbulence, and again, that's done kind of a hand-waving way here, where you say that the turbulence, that's just like local motions within the disk, are somehow on the same order as the scale height. And if you do that, you can get this and say that the turbulence is on the order of the scale height, and the turbulence velocity is around the sound speed, and you can recover this viscosity that way. Scale height, sound speed versus this omega. It's a different omega than I did before, where omega is GM to the 1/2 over r times r to the -3/2. Again, dependent on mass here. Now, these are the kind of models typically invoked, but these alpha disk models, alpha being this coefficient, are thermally and viscously unstable, so people tend to invoke something else to maintain the stability of that. And what they do is they assume that the viscosity is proportional to the same coefficient times the gas pressure. And these are so-called beta disk models, and these have the advantage of being both thermally and viscously stable. And here, then, you can look at the total pressure in the gas in the disk, which is the radiation pressure plus the gas pressure, and set this equal to density times the sound speed squared. So that's one way to look at this. Now, these thin disks are typically radiatively efficient disks. So you're getting radiation out of the disk you're getting energy out of the disk by radiation. But if the energy can't get out efficiently by radiation, you end up with a puffy disk. And those are radiatively inefficient disks. These are the so-called advection-dominated accretion flows. So in certain cases, people say you've got one or the other, depending on the accretion rate of the object. So it turns out these ADAFs may actually be prevalent in kind of lower luminosity or less bright HN. So that's a little bit of background what we're looking into, but what do we actually see? Are there black holes at the centers of galaxies? Well, what you can look at is rotation curves, and rotation curves give you a mass of a galaxy. So here's a non-active galaxy, and this is based on atomic hydrogen velocities. Here's a rotation curve, so you're looking at the distance from the center of the galaxy in kiloparsecs, velocity in kilometers per second, and this is a typical kind of spiral galaxy rotation curve, where you get this part in here where the velocity increases with distance, and then it falls off a bit here, and then it flattens out. So this is sort of a solid body rotation curve that's typical in inner parts of galaxies. You end up being Keplerian about here, and then this is that nasty dark matter stuff that causes this. Okay? All right. And you can look at near-infrared studies of stellar kinematics in the Milky Way. More has been done to this slide. And based on all this stuff, independent down in here, where it doesn't affect stuff at these larger distances, we can look at the stellar kinematics in our own galaxy and see that there must be a mass in there of about several times 10 to the 6 solar masses in a region that's less in size than the solar system. And again, invoke that, we have a black hole in our own galaxy. Now, if you look at elliptical galaxies, you can see all kinds of absorption features of elliptical galaxies. And these are basically stellar absorption features, and they're all velocity broad. So if this was an individual star, it would be quite narrow line. But if you're looking at a bunch of stars in stellar motion, so these lines get broadened out. So these things indicate that the stars in this elliptical galaxy are moving around some central potential. And from that, you can estimate what they're exactly moving around. And it's a variety of ground-based spectra. Some are STIS spectra, depending on the object. STIS is a Hubble instrument that can actually look at these bigger wavelengths with better spatial resolution. And there is STIS. This is an image made from the early release observations of the Space Telescope Emission spectrograph, which is installed in Hubble in 1997. This is 1998 Astrophysical Journal letter. And this is a false color thing of nitrogen-2, forbidden nitrogen emission, in the center part of a giant elliptical galaxy. This time it's M84. There's a disk of gas in the center part of this galaxy. And you can see here that this signature of velocities are increasing as you get close in, and again, as you get close into the central potential. The large velocities, both blue shifted and red shifted here, indicate the presence of about a 10 billion solar mass black hole. I think this actually, there have been other observations that revised the black hole mass for this object up a bit from these initial ones. So what happens is you've got a disk of gas here, the inner parts of the disk are moving very rapidly. From that, you can determine what the mass within that point might be. And from that, you can infer this kind of a mass. So, again, more or less high quality, if not direct evidence of the presence of a supermassive object at the center of that particular galaxy. Okay, it turns out that all galaxies, we talked about galaxies can have a central bulge of stars and then a disk, where an elliptical galaxy is just a big bulge. And anything with mass with a bulge, and even some without, has supermassive black holes. And this is just like a Hubble quotes tuning fork diagram. I don't know if you all know what a tuning fork is. It's a thing that you hit it, vibrates. But in any case, it looks like this. Looks like this. So this is just classifications made by Hubble of particular different kinds of galaxy shapes or morphologies. These are elliptical galaxies to the left, and spiral galaxies of various types to the right. And you can see in each of these, there is a central bulge, sometimes more clearly seen than in others, but you can see that little dot there and there and there and there. That's easy to see here because how stars are distributed in elliptical galaxies, but clearly there's more things at the center than there are further out, and that's why it's brighter in the center. And so any of these that have these sort of center concentrations appear to be harboring a supermassive black hole. And so, it's hard sometimes to get the black hole masses, and there's other mass in the bulge, massive stars, for example. But you can use those stellar velocity dispersions. That's the widths of those absorption lines from the spectra that I showed you 2 slides ago, to figure out how those velocity dispersions might be related to the black hole mass. And here, you can look, it's hard to see, this is velocity dispersion in kilometers a second down there. And this is black hole mass. You can see a pretty linear relationship between those two things. It's also related to the bulge mass in terms of how bright the bulge is. So the velocity dispersion gives you the gravitational effect of the bulge. And you can look at the starlight from the bulge. And you can compare the black hole mass, if you can get it in some way, to either of these things, and you get linear relationships. So this is important because it means that somehow, as the amount of stars in the bulge increase, the mass of the supermassive black holes contained within increases as well. So this is telling us something very profound about the evolution of galaxies. So how do you get the thing in the center? Well, I talked in the first slide about the Cygnus X1. If you have a large star that's large enough to overcome neutron degenerate pressure, that will form a black hole at the end of its evolution. Those are like 10 stellar mass black holes. The black holes you have in a elliptical galaxy like M84 are 1 billion solar masses. So how do you make one of those? If you know, come see me, okay? We can talk about it, because I have no idea. I just know that they're there. And so presumably you get stars die off, you get winds from stars, somehow that mass accumulates in the center, and then the mass falls in the center well, and you get a massive black hole forming, and it gets bigger and bigger as more stars, and eventually what happens is you get an AGN, and the AGN lights up, drives material by radiation pressure or jets from the bulge, and the thing freezes. So you no longer make the black hole mass bigger, and you stop making stars. This is called AGN feedback. There's various types of AGN feedback. Quasar mode means radiatively driven, baryonic winds, radio motor jets. And both of these have been invoked to explain that relationship that I showed you before about the bulge mass and the black hole mass. But the details of how the black hole got all this junk here, with details before question marks, nobody really knows how you make one. Whether they were made before the galaxy in bulge form, how they were built up, were they built up from 10 solar mass stars, or were they built up from black holes that had 1,000 solar masses? Nobody knows. It's a hard problem, because there's no observational evidence that shows you how it works. But we can go back to AGNs, the supermassive black holes. Black hole fuel radiates at some fraction of Eddington. I don't know if I showed you the Eddington formula before, but it's 4 pi CGM, mass of a proton divided by the Thomson cross-section. And basically, this is how much energy the system, the accretion disk, can radiate while still accumulating matter. If it's radiating any more, the radiation overcomes gravity, and the stuff can't get into the central potential. All right? When we talk about this thing, this is the eta m dot c squared. Tells you about how the radiation is coming out. If the AGNs are involved in the evolution of galaxies, they must have been AGN in the very early universe. black holes must have gotten turned on. And you do see AGN at very high redshift. Most of the bright things you see at high redshift are star-forming galaxies, but there are AGNs at redshifts of like 5 or 6. So they do exist. And again, we talked about various kinds of AGNs. But to make all this work, mass outflow, either of jets or winds, has to be present in AGNs, and had to have been present in AGNs when the bulges were forming early in the universe. All right. So that leads back to the talk I'm going to give on Friday when I talk about mass outflow. But that's why understanding mass outflow has some sort of general relevance in astronomy and astrophysics, because it's essential to the evolution of the galaxies themselves. Okay, so understanding or trying to determine the mass of black holes relates back to looking at emission lines, which is what we like to do with active galaxies. Remember, that's how they were discovered. So here are line profiles of various active galaxies, and the ones that are interested here are the permitted line, the hydrogen recombination line profiles. And so they would be these. This is H beta for various different secret galaxies. This is just oxygen 3, which is interesting because it comes from a more distant region. And you can see the various different shapes. It says there's some structure to these guys. Some of the emission comes from the same region the O3 comes from. You can see that distinctly here. But some of it comes from regions that clearly there's no oxygen 3 because kinematically they look completely different. And those regions are the ones that are close to the black hole, the so-called broadline regions that I told you about yesterday, have dense gas where you collisionally de-excite all the forbidden transitions, and so all you see are the recombination lines from down there. And so the thing is, these are close enough that the light travel times for them from the accretion disk's radiation to where the clouds, if you like, of gas are, is rather short. The structure of the broadline region, or BLR, here is not well known, and there's various ideas of what formed it, but we're only going to use it as a tool now to probe the masses of the black holes. So we don't really care how it forms, although that's an interesting topic as well. So if you look at this, and this is something I'm going to talk about next lecture, which is photoionization processes. So you've got a accretion disk that's emitting ultraviolet X-ray photons. We're talking about that. That radiation is intercepted by gas, either close or far away from the system. And the more radiation you have, the more highly ionized the gas is. The less radiation, the less ionized the gas is. If you have essentially an infinite pool of gas, you don't really see the ionization effects, but you just see more emission. So as more radiation goes up, the emission goes up. You get more ionization of hydrogen, you get more hydrogen recombination lines formed. So the hydrogen recombination line should get stronger as the continuum flux goes up, and get weaker because we're having less ionization of hydrogen, so less recombination as the flux goes down. And so if you can trace that and look at a time lag between where those emission lines are, or where the emission lines, if you look at a time lag between the response of the lines and the response and the change in the continuum, you figure out how far the gas is because it's a light travel time. So here's what this goes back into the late 80s. People have been doing this for a while. And this is light curves of various lights. What they look for is a cross-correlation function. So what they do is they look for the change in whatever they're looking at in response, in comparison to the change over time in the continuum. And they turn this a cross-correlation function here relative to a continuum taken at 1350 angstroms. And so they're looking at light travel time. And basically you're looking at the recombination time of the hydrogen, which is 400 seconds for that kind of density. It was the densities we're talking about. So essentially, 400 seconds, they're going to respond essentially instantaneously once the continual radiation changes in intensity as it hits the gas. Because it's so dense, it just responds up and down. So the lag is not due to the physical properties of the gas so much, but just its distance from the source of the radiation. All right? And so there's various things you can look at. Here's some lines. This is climate alpha, carbon 4 H beta. By the way, these are all done in the ultraviolet with a now defunct instrument called the International Ultraviolet Explorer, which was able to dedicate a lot of time. This comes from Brad Peterson's book on astrophysics, which is quite a good book if you're interested in this. And so what they do is they do something that's suggested by some years ago called Reverberation Mapping. And at a simple level, observers over here, you got some system over here, and you got some source of radiation. And you can think of the change in the flux as a delta function. Initially, in the most simple case, the flux just goes up, and then that radiation, an increased radiation, expands out to the region around it, and then the gas clouds, because they're so dense, respond immediately. And so you get, if you have a thin spherical shell broadline region, very simple case here, ionized continuum reaches the shell, it responds instantaneously because of the high density, and then the different surfaces get to the observer with different lags based on their position here. Okay, so you have the time delay and plus this 1 plus cosine theta. So it becomes paraboloid. And the intersection of the shell gives you an annulus for the surface area of this particular form. And if the emissivity is the same at all locations, you can get an emission line response function. So you're waiting to see how the emission lines will respond. Turns out if the emission lines were different pieces around, or parts around this black hole, different parts of the line will respond differently. So very simply put, say that the fastest moving gas is closest to the central potential. Make sense? Okay? So that would mean if you look at the wings of the profile of the line, that's where the fastest moving gas is producing. So if that's the closest, that should respond first. The core may be further away. Some of the core, some of the maybe in the sense that you're not getting it Doppler shifted, but some of the core is further away of the line, low velocities. So overall, that response is going to be more damped out when delayed. So fast stuff goes first, and then the core goes later. And from that, you should be able to recover the shape of the thing. We'll get to in a minute how that gets you a black hole mass, okay? And so here you go. You end up with this transfer function in emissivity. It's basically the radiation transfer of the broadline emission here, as this form here. And your time, your tau here, which was given before, is if there was no distribution, it would just be the R over C, the delay time, but you've got this distribution based on that. So you've got cosine theta for the spherical distribution. You can get a d tau, which is equal to that, and then you can figure out what the emission line light curve is based on this. I'm not going to go into detail, but you can set 2 points of tau equals 0, and tau being 2R over C, which is this travel time from the back end of the shell to you. So here you go. Here's the continuum flux. I said it was a delta function. So there you go. There's a delta function change times 0. Then you can look at the emission line response. So for a spherical shell of uniform emissivity with a delta function change in the flux, you get this rectangular change in emission line flux over time. And it's delayed. It's hard to see here, but you get a delay here based on the shortest travel time here. Now, it turns out, if you're looking at a sphere of gas, one part of it's going to respond for you immediately as the flux changes. And that's the part that's closest to you. So as the radiation is coming to you, you'll see the continuum radiation. There's a lag time to the continuum radiation in that piece of the shell, but they basically both happen at the same time for you, because you're looking at them together. So that part of the shell, that and the continuum, go up and down together, as long as the gas responds immediately. Then you have...
So turning off was called the same time.
Yeah. And then the back part of the shell, that's delayed. So the continuum will respond before the radiation, the distant part of the shell gets to you. This apart, though, is a pain, because any kinds of signal-to-noise problem, low-quality spectra, make it hard for you to figure out what's going on. So you need very high temporal resolution, because these things change on very short time scales. And you need a lot of dedicated time. So if you're looking at something, you have a gap in your observation, and that gap in your observation occur at a particular time, like a light travel time in your system, you are out of luck. So you have to have continuous coverage. So it's not an easy experiment to do. You can actually get the cross-correlation function here, which is what I was talking about before, which is this line luminosity times that. And here's kind of an average lag. And that's kind of the best thing you can do there. The thing I showed you before show the changes in the continuum and then a lag time for the radiation from the emission lines. And as Peter said, it can be shown that this thing here is also equal to this transfer function, where this is the continuum itself rather than the lines. Okay, so they tried to do that for a secret galaxy here, and it was complicated. I'm not sure what they got. And they got a lack of response at time 0. Remember, I told you there should be a line response at time 0 because that's the stuff that's right in front of you. Well, there's either a lack of gas there, or the gas is optically thick at that point, so it never responded. We don't know at this point. So what we should have had before was an immediate response from the gas in front of you and a delayed response. They got a delayed response, but no response from the gas in front of you, so that led to some confusion. It tells you how complicated this problem turns out to be. But when you finally have got all things together, all right, so the cross-correlation function gives you a characteristic size. This gives you the geometry. If you knew what the geometry was beforehand, you could relate this whole thing together. Now you worry about the kinematics, but the velocity, you get the velocity-dependent transfer function. And this is what I was talking about. Different parts, different velocities respond differently because the gas velocity is dependent on its distance. And so then you get a velocity-dependent profile, and this has never been done to date. And what they've done is they've modeled it so they have different distributions of gas here. I don't know where they come up with these distributions of gas. And it gives you different response functions based on that. And so the plan is to observationally determine this and compare it with models. They've had a lot of Hubble time to do this, and they've yet to do it really successfully yet. Okay? So they don't know what the distribution is, and actually this guy, Keith Horn, has worked out a bunch of models of response functions based on distributions of gas. In any case, it's a complicated problem, but even so, you can get a rough estimate based on the cross-correlation function, what the positions of the gas happens to be. Now, how do you get the black hole mass? Well, if you have some idea where the gas is distributed, and you know what the velocities are, then you just use Newton and Kepler to get the central mass. This is far enough outside the black hole's sphere of influence, you don't have to worry about general relativity. So you just get a mass essentially directly. So if you know the gas is this number of light days away and it's going this velocity, then you know what the central mass is. It's as simple as that. All this complicated stuff, the cross-correlation function, the transfer functions, notwithstanding, if you had all that, once you get to the end of this rather painful observational process, you have a very, very simple calculation to do. So, there you go. But since we don't know anything about distribution, they put in a factor in here that depends on kinematics and things like that. They get time lags here. They get the full path maximum from the line. This they get from they get a bunch of masses of black holes versus bulge mass reactive galaxies to get that F factor there compared to with galaxies that are not active, where the black hole masses are determined state by stellar kinematics. To make these two things match up together, they figure out what this F is. And this whole process, by the way, I haven't told you, is called reverberation mapping. So this is the reverberation mapping, is looking at the response over time. That's the reverberation. And here's a 35 reverberation map, AGN, and you can see, if you remember, these follow the same kind of relation between black hole mass and bulge luminosity that the normal galaxies do. But now we have a whole different number of ones that can actually determine the black hole mass is. And because they're active galaxies, we know one part of the system. We know the size of the engine. Remember, the black holes, the AGN's activity depends on the mass of the black hole and the amount of fuel. By doing this, we found out what the mass of the black hole is. And then we can look and see how it's being fueled and see how that works in terms of the behavior of the AGN and its evolution. really light me. Okay, so the trouble is, to do these reverberation mapping campaigns takes a lot of observing time, and it's hard to get. And you want to look at things that are going to respond well. If you look at ground-based telescopes, you don't have the kind of emission lines that really are going to give you a good map of this thing. You have a Balmer beta, but again, you got a lot of other contaminants in ground-based stuff. Often you can't see the continuum quite directly if you're looking at UV. You can see the response. The ionized continuum is more closely connected with the ultraviolet continuum, and it changes. But they've worked out ways where, based on reverberation map ones, they have a formula now. You can relate certain properties to get the black hole mass here. And this is a scaling relationship. It's the radius luminosity relation. So you look at the width of the H beta line, the continuum flux at 5100 angstroms, and some numbers here, and you can get the black hole mass. And these are called, if you just had one measurement, which is the continuum and the line width at one particular time, you don't have to have this thing sampled very tightly over time. You have one observation. These are called single epoch black hole mass estimates. And so this is much more efficient. The question is how accurate. It's, again, it wiggles around a bit. All these things are accurate to maybe a factor of 3 or 5. They're not, I mean, you can make that smaller by doing more, better sampled, longer period of time reverberation mapping, and then go recalibrate this. So, but that's kind of the work that you're dealing with now. But we have an idea of what these black hole masses are. And in terms of active galaxies, they range from about 10 to the 5 solar masses to about 10 to the 10 solar masses. For example, our Milky Way, which is not particularly active, although it seems to be being more active lately, it's a few times 10 to the 6. Seyfert galaxies range 10 to the 6 to 10 to the 8 solar masses. Some of the more luminous quasars can get up to beyond 10 to the 10. These radio galaxies have 10 to the 9 or 10 to the 10 solar mass black holes, but they're probably fossil quasars. So quite a range. But now what about the accretion disk? So now we have black hole masses. Can we go figure out what's going on here with the spin of the disk? Remember, all those metrics had black hole masses in them. So how do we get the spin of the disk? Why is that important? Well, if you're interested in radio jets, you want to know the spin of the disk. But again, the spin of the disk is telling us something about the evolution of the system. How did the black hole form in the first place? Conservation of angular momentum suggests early on it's going to be spinning quite rapidly. Does it lose angular momentum over time? This happens with stellar remnants like pulsars. They slow down as they lose their energy. So that would be quite of interest. So how do we get to that? So we can use emission from the accretion disk, this iron K alpha, as a probe of the disk conditions. Basically, iron K alpha, this is for iron 24 and lower ionization states. Iron goes up to iron 26, remember? And basically what happens is, it's an inner shell, it's a K shell. That's the innermost shell of the iron atom. An X-ray goes in and liberates an electron from the K shell, and that follows by fluorescent radiations. This is an example of the Auger effect. At higher states of ionization for 25 and 26, you don't get this, and all the K alpha is produced by Compton combination. And actually, the energies of these lines is different from these lines. You need high column density, so that molecular torus I talked about, broad line clouds, or the accretion disk would be an interesting one. Near the black hole, if you're out at the broad line clouds of the torus, you're away from the influence of the black hole. And so the lines tend to be fairly narrow, and we see that a lot. We see narrow K alpha lines. If you're close to the black hole, you should see the relativistic effects that I was talking about in the other slide, due to beaming and broad red tails, special relativity and general relativity. And so the overall profile is the one I was talking about before, and it's a function of black hole mass and spin. So if we got the black hole mass from reverberation mapping or magical single epoch things or whatever, or somebody told us, then if you can actually look at the K alpha line and measure its profile and look at how much the red end of the line has been stretched out by general relativity and how much the blue end is peaked, and you know the your line of sight inclination to the system, which is another factor you got to put in here. You can determine things like the spin of the black hole. So, again, I haven't talked about the inclination of the system. That's not necessarily an easy one to get for this kind of a study. And so people tend to look for other things for inclination for AGNs. So remember I showed you the picture of the bicone of illumination before? That tells you, if you can map that out, what the inclination of the black hole accretion disk system is. Because that and the surrounding torus is going to collimate the radiation. If you've got a radio jet, that radio jet material is going to be accelerated close to the black hole, highly collimated, and will go out and show you the projected vector, if you will, of the rotation axis of the black hole. So if you have that, you can figure it out. Otherwise, it's a little hard to do. You need some other way to figure out what the orientation is. There are a few other ways to work these things out as well, but you need some other independent way to get the inclination. Or you can just like plug numbers in for inclination and figure out whether you got the right answer or not. So this is what you're looking for here. And so here are some models of what you should see. It's kind of like what I showed you before on that slide of prograde and retrograde motion, but here in more detail. And these are for different angles of inclination. Okay? And so here we're going to use, instead of the Schwarzschild radius, we use what's called the gravitational radius, which is basically 1/2 the Schwarzschild radius. Okay? So we do this in terms of gravitational radii, and you can look at this. This is a Schwarzschild disk. And you can see this is shaped here, and this kind of double peak thing here, and this broader double peak, the lower peak here. This 10, 30, and 60 are angles of inclination. Okay? Now you can look at a curved disk at a couple different angles of inclination. You can see at some point, this one looks pretty much like that one, but if you get the right angle of inclination here, this thing is very, very broad. The reason the curved one gets very, very broad is your innermost stable orbit in that case, and this of course would be a prograde motion, not a retrograde motion, is now very close to the event horizon. And so gravitational redshifting is extremely strong. You get this big tail. And you can see from your question here that this case and this case are identical, and that's one from further out. So if you're at 4.5 gravitational radii, it doesn't really help you too much if you're doing it. That would be the case, for example, for retrograde motion. So it has observational consequences that you really can't sort out the retrograde, but you can sort out the prograde motion. And so here, the innermost stable orbit is 6 Rg versus 1.25 Rg. This was 6 Rg. 1.25 Rg is at the inner edge of the disk. So now you're approaching the Schwarzschild radius. Okay? And you get this kind of an effect. Does it work? Not really. In spite of what people claim, the solutions are often degenerate. So here's the case. This is by a colleague of mine that Hanata knows well, Tahir Yaqub, a good guy. And Tahir is at Goddard Space Flight Center. Farewell 9 is a very luminous Cipher-1 galaxy. It's almost a quasar. And so basically what happens here is, this is what he observed. This is done with a Chandra high energy transmission grating. So it's a very high resolution X-ray spectrum. And so when you're in the range of the iron K line, it can resolve the structure of the K line. There are other instruments that are sensitive in that area, but they don't have the resolution. So there are a couple other X-ray satellites, Suzaku, who's now defunct, and New Star, that are sensitive in this range, but the resolution isn't very good. The one that was really good got one observation, and then it went, because of let us say, human error, was destroyed, and that was the Japanese Hitome satellite, which really could have resolved this even better than Chandra. But up until now, Chandra's what we got. You can see what the here found is this double peak here. 6.4 keV is the energy that you would get at rest for the K alpha fluorescence. So this is what he gets here. And so what he did here is he plugged in a couple of different angles here and a couple of different radii here, and he got these particular shapes here. He found out, given the quality of the data, he couldn't tell exactly where the thing was. It's somewhere, it could be 6 gravitational radii out or somewhere inside 6 gravitational radii out. But the data weren't good enough, and his ability to determine the angle of inclination wasn't good enough to really sort this out. And actually, an object like Ferrel 9 doesn't really have any really extended radio jet or extended narrow line region because it's pointed in a way that those things are foreshortened. And so you really have a hard time figuring out the inclinations. It's kind of face on, but it's hard to tell. So the answer is it's a very hard problem, and in spite of some comments based on data taken with NuStar and Suzaku that they have been able to determine the spin, it's dependent on a lot of assumptions that they really aren't really strongly supported, so it still is an open thing whether you can get black hole spin or not. But again, getting back to what the problem initially was, how do you make these things? Well, once again, we don't know. So here, just for fun, this is the LIGO different detections of gravitational waves over the last couple of years. And you can see these are little pictures of what the systems are. I guess these things are the relative masses of the coalescing black holes that formed all these things. And so you can see with the frequency here and the actual, profile of the gravitational wave disturbance that they detected was from all these different systems. And these are all, they're very large. I mean, they're like 30, 50, 70 solar mass black holes. And we don't really know how you make stellar mass black holes that big. Ones in the local universe or nearby tend to be things that are like maybe 20 is the maximum solar masses. And that's smaller than almost all of these. People feel that maybe very old populations of stars before they had reprocessed material, so-called population 3 stars, could make black hole masses this big. Something must have made them, or they were built up by, in other cases, from other black holes coalescing to these sizes. They don't know, but these are orders of magnitude, many orders of magnitude beyond what we see in the supermassive black holes in galaxies. So they detected gravitational waves for these things, but we don't know how they built up. We said, what if, can we point LIGO it and see if we find coalescing black holes from galaxy-sized black holes? I showed you one that might be 3 that were coalescing in a slide yesterday's talk. Well, the frequency of the gravitational waves is beyond the detectability by LIGO, so you can't detect those yet. Maybe spaceborne experiments, LISA, I guess, is the spaceborne one, might be able to detect those. I don't know. But nothing we've detected so far can make the kind of black holes that we see that are there. So we know they're there. We know they obey, general relativity. We can see some general relativistic effects. But sorting out the details, even getting the spin of these things, has so far been a bit elusive. Getting the masses, we can kind of do that with some errors. But we know they're there, and we don't know how they got there. And that's the answer.